All right, so let's go ahead and debrief the first page. All right, so keep in mind that the values that you're seeing here are likely going to be different than what you and your group produced, because the results of your 50 tosses are going to look different than the results of the 50 tosses that I did. In question number one, our point estimate is essentially just the fraction or the percentage of our tosses that landed flat. So for me, that was 19 out of 50, or 38%. Of course, for you, it'll be slightly different. But the one thing that I want to make sure that we all do here is we add on the notation for this value. Okay? So this is a sample proportion, so we should be labeling it with the notation p hat. All right, in question number two, we're describing in context some of these things. So the population would be all tosses. Now, some students want to say all Hershey kisses, but we're really interested in what happens when you toss the Hershey kiss. So make sure that you have tosses there as your context. The sample is the 50 tosses that you and your group did. The parameter, so this is the thing that we're interested in estimating. We want to know the true proportion of tosses that land flat. Okay. Now, let's go ahead and add some notation there. Okay. So because this is describing the true proportion, we're going to label this as P. Okay. And then the statistic, of course, that's just our point estimate, and I'm going to relabel that as P hat. All right, question number three. Was the sample random? Yes, it was. We can think of each toss as completely random. Okay. Now, why is it so important that we have a random sample? Okay. And the reason is we want to be able to generalize the results from our sample to the entire population, right? We want to say that what we saw in our sample is representative of what we would see if we did the whole population, if we did all possible tosses. All right, so in the future, we're going to just refer to this as the random condition. And this is just one of the things that has to be met in order for us to create a confidence interval. All right, question number four, what's the formula for the standard deviation? So you can look on the back wall at the Reese's Pieces poster, and you can get the formula off that poster there. All right, now to use that formula, there is another condition that has to be met, which is the 10% condition. Okay, so that is the sample size has to be less than or equal to 10% of the population. So for our case, our sample size was 50 tosses, and that is clearly going to be less than 10% of all tosses, because really there's an infinite number of tosses if you're thinking past, present, and future. All right, so why is this so important? Well, for most cases, when we sample, we do it without replacement. So this 10% condition is just saying that sampling without replacement is okay, and that it's not going to affect our calculations, our probability calculations too much. Okay. So I'm going to write the reason here. So sampling without replacement is okay. All right, so this is another condition that has to be met before we can even think about constructing a confidence interval. All right, from now on, we're just going to refer to this as the 10% condition. All right. Now, question number 6 is a really important part of the activity. Okay, so we want to calculate the standard deviation for our sampling distribution, but we don't know the value of p. Right? Remember, p is the true proportion, which we don't know. We've got a sample proportion, but we don't know the true proportion. Okay? So what we'll do is we'll just estimate, right? We'll use our sample proportion in place of the true proportion. Okay? And so that's what it's saying to do here, right? Just use the value for p hat. All right? So for me, that ended up being 0.38. 1 minus would be 0.62. And then the sample size was 50. Okay? So I got this value. Of course, remember your value is going to be a little bit different. All right. Now, because this isn't the true value of p, then this is not the true standard deviation. So we have another name for it. We call this the standard error of p hat. Yeah. And that just simply means it's an estimate, or it's our best guess for what the standard deviation would be. All right. So we have an expression here in numbers. Let me write an expression using notation. I'm going to have to slide this over real quick. All right. So what I did there was I took my p hat value, multiplied it by its complement, divided by the sample size, and then took a square root. All right. So the only difference is that the standard deviation formula uses p, the true proportion, and our standard error formula uses p hat, the sample proportion. All right. The notation for this is SE with a subscript p hat. Right, and then the SE is just short for standard error. All right, last question here on the front. Would it be appropriate to use a normal distribution to model the sampling distribution? So we know that we can justify this by checking the large counts condition. All right, so that's just the product NP and then the product N1 minus P. Okay. But we run into the same little problem, which is that P is the true proportion and we don't know what that value is. So we're going to have to use our best estimate, which is P hat. Okay. All right, so for me, that was doing 50 times 0.38 and then 50 times 0.62. Yours is going to be a little different. Okay, but hopefully you got two values that were greater than 10. Okay. All right, so yes, we're going to use a normal distribution to model the sampling distribution. Right. So really the focus of this first page was to remind you or reintroduce you to some of the conditions that have to be met in order for us to do these statistical analyses. Okay. So random condition, 10% condition, and the large counts condition. All right, so let's go to page 2, and we're going to do question 8 as a whole class. Okay. All right, so first it wants us to write out the general formula for a confidence interval. We learned this in the last activity, right? It starts with a point estimate. And then we need to include or incorporate a margin of error. Yeah. So the first example that I gave you was I was trying to guess Alex's birthday. I think my point estimate was July 1st, okay? And then I used a margin of error of 2 months, right? So really, my estimate was the set of dates between, let's see, July 2 months earlier would be May 1st, and then July and 2 months later would be September 1st, right? So May to September 1st was my set of guesses. All right, now, one question you might be wondering is, well, how do we figure out the margin of error, right? Why do plus or minus 2 months? You know, why don't the guessers do plus or minus 3 months or plus or minus 1 month? Okay. Well, when we're trying to estimate a proportion, right, the margin of error is simply related to how many standard deviations we expect our estimate or our sample proportion to be from the truth. So to think about, standard deviations from the mean, right, let's go back all the way to the first unit. Remember we learned about the 68, 95, 99.7 rule, right? Something like this, right? 68, 95, 99.7, right? So 68% of the data should be within 1 standard deviation, 95% within 2 standard deviations, and 99.7% within 3 standard deviations. All right, so for the first question here, right, we'll just write in 2, right? 95% is associated with being within 2 standard deviations of the mean. Okay. All right, so this value is called a critical value. right? It's basically telling us how many standard deviations from the mean for a certain percentage. Yeah. All right. Now, what we're going to do in question 8 is find some other critical values for some non-common percentages, so not 68, 95, or 99.7. Okay. All right. So let's say we want 80% of the data to be in the center of our distribution. We want to know what are going to be the boundary values or the critical values. Okay. So let's sketch a picture here. All right, so we're saying that we want, oh, too big, 80% in the center here. And that means we're going to have 10% in the left tail and 10% in the right tail. Okay. And so our critical value is going to be, we're going to use the right boundary value as our critical value. Okay, and that's just going to be some z-score. I'm going to put a little star next to it because it's a special z-score. Okay. All right, now there's a couple different ways that we can find this critical value. Okay. First option is we can use table A, right? This boundary value is associated with the 90th percentile, right? 10% and 80% makes 90% to the left. Okay, so we can go to our table. All right, and we can find the closest thing to 90%. All right, so it's that value there. Scroll to the left, and you see that the z-score is 1.28. Okay. All right, so we can write 1.28. All right, well, that's the old school approach to doing it. Okay, the new way of doing it is to use your calculator. All right, so rather than look up the 90th percentile in table A, you can just use the inverse normal function on your calculator and type in 0.90 for the 90th percentile. Okay, and when you do that, right, and you run the function, it'll tell you what that critical value or what that boundary value is. So 1.28155 gives you lots of significant digits. All right, so we'll just say 1.28. So let's record that here. What happened? Delete. Okay, 1.28. All right. So what if we wanted, 90%? Okay, well, now our picture is going to change. All right, so now the middle here would be 90%, and we'd have 5% in each tail. Okay, so our boundary value has a percentile of 95. Right, we're adding the left tail and the center because that's what's to the left of our boundary value. All right, so on the calculator, we can just type in the percentile, 0.95. Now, if you have a newer calculator, right, you do have the option of just selecting center, right? So in that case, we would just say, all right, we want 90%, and then you'd select the center. Okay. But if you've got an older calculator, like all the yellow ones that are floating around the room, you don't have the option of selecting left, center, or right. It always does left by default. Okay. All right, so I'm going to just set it up that way. So we've got 95% to the left of this boundary value. Okay, and then after you run that, you get this z-score, 1.6448, which we can round that 1.645. All right, now let's reset up the problem with 95% in the center, right? Now you're thinking, oh, why do we got to do that? We know it's going to be 2. Well, not really. Kind of a lied or I guess the term is gatekeeping. I was gatekeeping you. This is only an approximation, right, that it's 2 standard deviations. Okay. We're actually going to look up the precise value here in just a minute. All right, so let's redo this so that we have 95% in the center, meaning 2.5% in each tail. Okay, so our boundary value now has a percentile of 97.5%. Right, we're doing 2.5 plus 95. All right, so set it up on your calculator, right? Inverse normal, set the area to 0.975, and then this is what you should get. Okay, it's not quite 2. Okay, it's 1.9599. So let's call it 1.96. So this is what College Board is going to want you to use, right? This more precise value. Don't use 2 anymore. All right. Final one here is if we have 99% in the center. So for our picture now, we'll write 99%. So we're going to have 0.5% in the left tail and 0.5% in the right tail. Okay. So our boundary value, though, has 99.5% to its left. Okay, so set up your calculator. So the area is 99.5%. And the boundary value or critical value is going to be 2.575, which I'll just call 2.5, let's say 2.576. All right, so now we know how to find these critical values. You first decide how confident you want to be, and then once you've selected a confidence level, then you can use table A, or probably better, just use inverse normal to look up what critical value to use. All right, so I'm going to ask your guest teacher to pause the video here, right? Give you a chance to do the rest of page 2 with your table. Okay. Now, when you get to question 11, it wants you to sketch your confidence interval on the board. So if somebody could just draw this number line on the sideboard, and then you guys can draw in your confidence intervals as you compute them. All right, so pause the video, and then when you're ready to do the debrief, unpause it, and we'll talk about page 2. All right, so you finished page 2. Let's talk about these calculations. Okay. All right, so in question number 9, you are figuring out the margin of error, right? And they tell you how to figure it out. You multiply a critical value times the standard deviation or standard error from page 1. Okay. All right, so for 95%, our critical value is going to be 1.96. My standard error, now mine's different than yours, but I had 0.069. Yeah. All right, so this is now my margin of error. All right, go ahead and do this. Let's write a formula both in words and in symbols. Okay. So the margin of error is equal to the critical value times the standard error. Now, in notation, right, the critical value, we're just going to write that as Z star. It's just a special Z score. And then the standard error, the notation that we used earlier was capital S, capital E, subscript P hat. All right, cool. All right, now that you have the margin of error, you can take your point estimate, add and subtract your margin of error to get the endpoints of your interval. Okay. Now it's walking you through it. It's reminding you that there's this general formula. Okay. But let's write a specific formula. Let's turn these numbers into statistical notation. Okay. So 0.38, how can we represent that? Well, that's our sample proportion, our p hat. Okay. 0.0135, or whatever value you got. Okay. That was the result of the previous question, right? So that was the z-score times the standard error, or essentially we can use this notation here. But I'll take it one step further, right? Let's replace the notation SE p hat with the actual formula, which was back here on page 1. Okay. So I'm going to go ahead and copy this and move it down, right, in place of that notation. Let's resize that just a little. All right, so we've got our point estimate plus or minus our critical value times our standard error. Okay. This formula is referred to as the specific formula. Right. You will only use this formula when you're trying to estimate a proportion. All right, I have no idea what your confidence intervals look like, so I just had to make something up. So let's say that these were the intervals that we got from every group. Okay. All right, so based on these intervals, you know, what do we think the true proportion of kisses that land flat is? Okay. Well, obviously 80% wouldn't be a good value, right? None of the intervals would support that value. Okay. 10% wouldn't be a good guess either, right? Again, none of the intervals would support that value. Okay. 30% might be okay, but not every interval supports that, right? That one doesn't support it, that one doesn't support it, right? So only a handful of intervals would support 30%. Okay. Same thing, 50% is only supported by some of the confidence intervals, right? So our best guess should be a value that is supported by all the intervals. So like 40% would work, 39% would work, maybe even 38 or 41. Right? Anything in that neighborhood would seem like a reasonable value. Okay. But here's the thing. We don't really know. We'll never know the truth. Okay. There's no way that I could figure out what the true proportion of Hershey Kisses tosses that would land flat. I can't toss the whole population. Okay. So we'll never know. Okay, never know the truth. Okay, we'll have a guess, we'll have an estimate, but that estimate is not the truth. All right, let's flip over to the last page and do a quick summary. So this was a two-page activity. The first page focused on the conditions. Okay, so they're numbered here. Number 1 is the random condition, so you've got to have a random sample. All right, so no convenient sample, no sample that has any sort of bias in it. We want it to be random so that it's unbiased, so that it's representative, so that we can generalize the results to the population. All right, condition number 2 is a 10% condition, which needs to be done when you sample without replacement, which is almost all the time. So you're going to check that the sample size is less than or equal to 10% of the population size. Yeah. Condition number 3 is large counts. Right? We're checking the large counts to justify the use of normal distributions. Okay. Now in the past, we said it was NP greater than 10 and N1 minus P greater than 10. But in this situation, we don't know the true value. Okay? So we have to use our best guess, our estimate, which is P hat. All right, so those are the conditions. All right, now let's talk about those formulas. The general formula, right, it's just written in words, right? Point estimate plus or minus a margin of error. Okay. And then that specific formula uses p hat as the point estimate, and then it uses a special z-score as the critical value, and then it's the square root of p hat 1 minus p hat over n, which we call that the standard error. Okay. So I'm going to add a couple extra labels here, right? So that's the standard error, and that's the critical value. Right. And then combined, that gives you the margin of error. Okay. All right. If there's time, let's go ahead and pause the video one last time, get back with your group, and work through the check your understanding question. There's 4 parts to it. You might want to refer back to some of the older activities when you're doing things like interpreting the interval, right? Go back and look at the template for writing the interpretation. But yeah, go ahead and work for about 5-10 minutes and then unpause the video to check your answers. All right, so here are the answers to the check your understanding question. Right, so we can leave this up on the board, and then I'm sure the period's going to be over pretty soon, so I hope you guys all have a great weekend.